Number 18 is a pretty interesting problem, and it looks pretty complicated. One of the first things that we're going to do to simplify this is we're going to separate this into two different integrals. So since we have two different terms, we know that we can integrate each of those terms separately. So we're going to integrate, first of all, x times e to the x squared power with respect to x, plus, then we'll integrate this part separately, so e to the x divided by e to the x plus 6 dx. So we're going to integrate each one separately. I'm going to draw a line to kind of separate a little bit. Both of them are going to be solved using the substitution method. So for the first integral, I'm going to let u equal the exponent for e. So I'm going to let u equal x squared. And then we have the du. That would be 2x dx. So let's look at what we have and what the extra part is that's floating around. Alright, so we have e to the u power. So the extra part that's floating around is the x dx. And this looks pretty close to the extra part that's floating around, except we need to divide by 2. Scoot this down a little bit. So 1/2 du is equal to x dx. So we're going to replace x dx, this extra part that's floating around, with 1/2 du. So we end up with integrating e to the u times 1/2 du. And of course we can bring that 1/2 out to the front and then just integrate e to the u du. Okay, that's pretty easy. So we end up with 1/2 times, and of course the antiderivative of e to the u is just e to the u. We'll put the plus c at the end once we figure out this part as well. So we'll stop there for a second, and then we'll come over here to this side, and we're going to let u equal the most complicated part of the second expression. So I would say that's e to the x plus 6, and then the derivative of u would be e to the x dx. So what we actually have then for this second term is something that looks like this. We have u at the bottom, and then we have e to the x at the top. So all of this is our extra portion that's floating around. And that matches exactly the right side of du, so we can replace that with exactly du. So we're going to put du off to the side. We can't leave the top empty, so I'm going to put a 1 at the top as a placeholder. Okay, so now I'm actually going to perform the integration here. The antiderivative of 1 over u would be the ln of u. And so what we have so far then is 1/2 e to the u plus ln of u. And then we'll put in our constant of integration. Okay, now at the very end here, I'm going to go back to actually using the original variable. So we're going to go back to x. So we're going to go ahead and represent what u is for the first part. That would be 1/2 e to the u power. The u power here for the first one was x squared, plus ln of, in the second part, u represented e to the x plus 6. And then we'll include our constant of integration. So we end up with 1/2 times e to the x squared power plus ln of that input x e to the x power plus 6 plus our constant of integration c. Alright, for number 19, we're also going to solve this by u substitution. We're going to let u equal the most complicated part of the expression, or something that's raised to a higher power. So in this problem, I'm going to let u equal ln of x. Let's rewrite this a little bit before we go further. keep in mind that what we can do is we can write this as 1 over x times 1 over ln of x cubed times dx. So I can separate the original integral like this. So what we actually have then when we go to do the substitution is something like this. We can replace ln of x with u. So we have 1 over u cubed. So the extra portion that we have floating around is 1 over x dx. So let's see what we could come up with. When we take the derivative of u, du is equal to, well, we get the derivative of ln of x is 1 over x dx. And that's quite convenient because the right side is exactly the extra stuff that we have floating around, so we can replace that with just du. Okay, and I'm going to go ahead and before we start to integrate, I'm going to rewrite this as integrating. I'm going to bring the u to the top, write that as u to the negative 3 power du. Okay, so now we're going to actually perform the integration. I'm going to add 1 to the exponent. So it gives me u to the negative 2 power, divide by the new exponent, and then add the constant of integration. Okay, the last thing that we do is go back to using the original variable that was used at the very beginning of the problem. We're going to go back to x. So that would be u to the negative 2 power divided by negative 2 plus that constant. So u actually originally represented ln of x, so I'm going to put ln of x in place of u. So get ln of x raised to the negative 2 power divided by negative 2. And if I wished, I could rewrite this. So you could stop here, or we could rewrite this with positive exponents if we wish. So I can write this as negative 1/2. So think about kind of like this is 1 over negative 2, so negative 1/2 times and I'm going to bring that ln of x to the bottom of the fraction. So I'm going to write this as times ln of x, all of that raised to the positive 2 power, plus c. I'm going to write this a little bit bigger. So we can't leave the top empty, so that would be negative 1 over 2. And then we brought the ln of x down to the bottom of the fraction, give it a positive exponent of 2, and then our plus c. Of course, you can put that 1 in the middle. It looks a little bit nicer.